Hello, this is Hariharan Tyagarajan from Kansas State University. This talk addresses some of the challenges of critical system development using model-based engineering and how an information flow analysis framework can address some of these challenges. AADL is our choice of modeling language. It is a SEA standard modeling language used in aerospace and automobile industry. In later part of this talk, I'll present our information flow analysis framework and demonstrate its capabilities using an unarmed aerial vehicle system and how our tool can help visualize some of the security requirements. In recent times, critical systems have become complex and interconnected. One way to cope up with the scale is to adopt distributed development. When multiple stakeholders are involved, it is challenging to communicate the dependencies and responsibilities and also maintain common goals across stakeholders. In early modeling stages, when the system is evolving, it is essential to preserve critical properties. In a model based system engineering, when multiple vendors are involved, where one may develop the control system and the other develop the UI software, it is necessary to establish how the UI interactions impact the control system logic. In a security critical system, there can be multiple channels with varying levels of security. Properties such as non-interference has to be maintained by all the involved parties. Similarly, in safety context, tracking fault propagation and mitigating hazard is a collective effort. We believe a general information flow framework can be a useful tool to analyze, communicate, and maintain critical properties across the system. We present AWAS, our information flow analysis framework for AADL and EMV2. In the rest of this talk, we use a simple unarmed aerial vehicle system as our running example. This top-level system consists of a ground station and a UAV. The objective of this system is to perform surveillance in a given region. The ground station transmits a map to the UAV. From the map, the mission computer in the UAV develops a flight mission consisting of set of waypoints. The UAV navigates from waypoint to waypoint until the mission is complete. The UAV periodically sends status information back to the ground station. This is the top-level UAV system AADL model consisting of the ground station and the UAV subsystem. In AADL, a system can be developed using either the graphical or the textual editor. An AADL component consists of a component type section where the interface of the components are defined and a component implementation section containing the subcomponents and connections between them. This diagram shows the component implementation section. The UAV system model consists of 5 levels of hierarchy. From an AADL model, we derive two kinds of flows, intercomponent flow and intra-component flow. In this UAV subsystem, we can see components communicate either by accessing a common bus or directly communicate through port connections. Also, AADL includes connections that are responsible for communication between a parent and subcomponent. AADL also includes flow construct to specify the flow of information within a component. There are three kinds of flow construct. A flow sink is used when a component absorbs the information provided to it. Here, the flight controller consumes the waypoint to navigate the UAV system. Similarly, the component can also be responsible for generating information. The flight controller generates position status to update the ground station. This is captured using a flow source construct. There are components that process the information it receives to generate the result, such as the mission computer, which processes a map to produce a set of waypoints. A flow path construct is used to capture the dependency between the input and output ports involved in the component. Using these information flow specified in the model, we compute a dependency graph on which we perform various reachability analysis and render the result as a HTML5 interactive visualization of the model. The HTML visualizer is a standalone portable model explorer usable without installing AADL modeling IDE called OSATE. Our visualizer can expose properties associated with other AADL annex in the model. A typical component of our Awas visualizer consists of a list of inputs, points where information flow into the component, and outputs where information flow out of the component, and flow paths capturing intra-component flows. Awas visualizer is a single-page web application with an ability to explore and view multiple subsystems side by side. The primary function of Awas is to answer reachability queries. For example, in the context of UAV system, if the analyst wants to know when the ground station sends the map, where does the information regarding the map flow? Also, where is it getting consumed? Using Awas, we can answer such queries by selecting the component or port we are interested and clicking the forward button. Our tool computes the reachability and projects it on the graph. From the port sent map on the ground station to the port receive map on UAV, there is the little icon on the UAV component that indicate that it has subcomponents. By double clicking on the component, we can open it. Here is a quick demo of the visualizer. Here I can select the send map and perform the forward analysis. Also double click on the UAV to open the subsystem. I have opened all the 4 levels of subsystem here, and I can also repeat the same thing and see the information flow in all the subsystems. In our UAV system, there is a possibility that the ground station can be compromised, and an adversary can use the ground station to attack the UAV, either to capture it or crash it. To avoid such situations, we have developed a filter to discard malformed commands and provide only well-formed commands to the flight controller. However, we have to ensure only well-formed commands reaches the flight controller. In our model, we want to check that all communications from the ground station first reaches the filter before reaching the flight controller. To check these requirements, we have developed a simple domain-specific querying language. All our query languages are of the form query name equals query expression. We use the query name to identify the result of a query in an audit check, also to support using the result of one query in another. The queries are interpreted in the browser itself. Using these queries, we can perform the basic forward and backward reachability. We can compute the reachability between 2 points, such as from a source to sink. Also, we can enumerate paths from a source to sink, satisfying simple constraints. Here is the quick demo of the query view. Here, there are 2 parts to it. One, the query interpreter, and the other is the query table. The query table lists all the previously executed queries and stores the result. On clicking each of these query, I can visualize the result on the graph. I can also select more than one queries to see the results of both the queries and compare them. To check the previously described requirement, we can write the query with ground station port as source and flight controller as the sink. Also with the constraint saying without going through the ports of the filter. When we get an empty result, we know that there are no paths exist between the ground station and the flight controller without going through the filter. A quick demo to see this query in action. Here I have already written this query, and by clicking this query I can see that there is no result, meaning that there is no path exists from the ground station to the flight controller without going through the filter. With a compromised ground station, an adversary can perform nefarious action within the well-formed commands. To avoid such situations, we want to ensure only authorized ground station can communicate with the UAV. To check that we have to ensure each command comes from an authorized ground station. Without developing the implementation details of the authorization mechanism, using EMV2, we can abstractly encode the properties of the ports and check using AAWAS. EMV2 stands for Error Modeling Version 2 Annex. Is a designed to perform hazard analysis and risk management on AADL models, using which we can develop an abstract set of tokens each capturing a specific error domain. For example, if there is a component supposed to produce value between 0 and 1, we can call any value out of this range as value error. Using EMV2, we can also abstractly specify the error behavior of a component using the error flow construct. For example, there can be some internal failure in the component C and it can cause a value error on port P2, or the incoming error from the other component may delay its own processing and cause a late value. We can use this mechanism to develop a set of error tokens capturing the security properties, abstract behaviors of the filter component, and the data security property. We can model the command from the ground station can either be authorized or not authorized, and in the software subsystem, we can insert a checker that discards command that does not contain the right authorization token, thus ensuring only the authorized command reach the flight controller. Combining both the properties, we can check for only authorized and well-formed command reaches the flight controller. To do that, we develop distinct error tokens to capture all possible combination of authentication and well-formed properties and their failure cases. Using AWAS, we can visualize the information flow into the UAV and eventually to mission computer and software. Inside software subsystem, unauthenticated and malformed commands are discarded and only well-formed and authenticated commands reaches the flight controller. Here is a quick demo describing what happens when malformed or unauthenticated message commands are sent out of the ground station. Here I click on an unauthenticated token and I say forward to see that in the software subsystem inside the radio driver component we can see that unauthenticated messages are consumed or discarded, and thus the flight controller does not receive any unauthenticated commands. Similarly, a not well formed command from the ground station is again discarded by the filter, and thus the flight controller does not receive any of the malformed commands. However, when we when the ground station sends out a well formed and authenticated command, we can see that it reaches the flight controller. We can also accomplish the same thing using this following query. In this query, we have modeled the possible combination of authorization and well-formed commands as the error token and provided to the ground station send map port. Also, we have included the expected property on the flight control waypoint port. By executing this query, we will get the same result as we did using the button clicks. In conclusion, we have developed and demonstrated the usefulness of a general information flow framework both in safety and security context. In a recent work, we have applied AWAS to perform hazard analysis on OpenPCA pump medical device model. This is a realistic model with about 80 components and several hundred connections. In our experience, an interactive visualization tool is a useful in exploring and understanding large models. In future, we are planning to support additional security and threat modeling capabilities. We are also planning to enhance the visualizer to show coverage information from execution and testing, also the counterexamples from model checking activities. Thank you.